So in this particular video, we're going to elaborate the concepts of entropy. First of all, remembering what entropy is, just a quick review, is entropy is the degree of disorder of the system. And basically what we're looking at is the amount of freedom or movement the molecules can have. An increase in entropy is generally true in reactions where you're going from something that is solid or liquid to a gas. And the other controlling factor is that all spontaneous processes need to be accompanied by an increase in entropy of the universe. So for the first question, we have 2 moles of sulfur dioxide plus a mole of oxygen, and that is going to 2 moles of sulfur trioxide. So we have 2 moles of gas on the right hand side and 3 moles of gas on the left hand side. So we can say the change in entropy is likely less than 0, or in other words, it's a decrease. And the reasoning is simply because we go from 3 moles of gas to 2 moles. For question B, we have barium hydroxide decomposing into barium oxide and water, gas. The first thing I always look for is the states, and I have solid to solid, but solid to gas. So I'm expecting entropy to be greater than 0 or an increase. And the simple reasoning is the products have a gas. For part C on this question, we have carbon monoxide plus hydrogen gas producing methanol. So we have gas and gas going to a liquid. So delta S is less than 0 or decrease. And the reasoning is gas to a liquid, and a gas has the most entropy, a liquid has the next most, and a solid has the least entropy. So for question 2, we're being asked to look at the standard entropies at 25 degrees Celsius between 2 compounds. So copper 2 oxide is 42.59, and copper 1 oxide is 92.36. And these are both joules per Kelvin. Joules per Kelvin, and assuming it's 1 mole. The comparison between the two is that this one has more entropy, and the reason is very much just the fact that it has an extra atom. So more atoms means more microstates. As the number of microstates, which is symbolized by capital W, increases, so does the entropy will be greater. In this case, the change of entropy will be greater converting between the two. But the next is 1 mole of nitrogen dinitrogen tetroxide and 2 moles of nitrogen dioxide. N2O4 is 304, and 1 mole of nitrogen dioxide is 240, but we have 2 of them, so that's 480.9. Again, joule per Kelvin. So basically what we're looking at here is more moles means more disorder. And that's basically how straightforward that potentially can be. So in question 3, we're being asked to use Appendix C values. Appendix C values are standard state. So you'll notice that this is asking us to use standard state values, and that is indicated by the degree symbol. So we are just going to use Hess's law. So the change in entropy for the reaction is equal to the entropy of ammonia gas times 2 moles products, take away reactants. So 1 mole of H2, take away 1 mole of N2H4. The delta S of reaction is 2 times 192.5. Take away 238.5. And that's for N2H4. And take away 130.58 for H2. So the delta S of reaction is equal to plus 15.9 joules per Kelvin, which is a minimal change. Not much for us to actually look at or worry about. The only reason that this is even positive is because the molar entropy of hydrogen is only 130, which is quite small because H2 has very limited number of microstates possible. And it's very hard when you get 15.9 joules, because that change is so minimal that it kind of reflects what's going on in the equation, which is 2 moles of gas going to 2 moles of gas. There's not a lot of prediction we can make with this statement. We just know that it's probably going to be very close. For question B, we have potassium solid plus oxygen giving us potassium oxide. So delta S of reaction is equal to the standard entropy of KO2, take away the standard entropy of K solid, take away the standard entropy of O2. Delta S of reaction, just double check that it's 1 to 1 to 1. And I'm going to look up KO2, which is 122.5, take away 64.67, take away 205, and this equals negative 147.2 joules per Kelvin. So negative 147, well, let's look at this. We have a mole of gas on the reactant side and just solid on the right side. That is a definite decrease in entropy, and that's what our calculation reflects. A decrease due to the loss of gas state. So finally we have magnesium hydroxide plus hydrogen chloride, it's gas, going to magnesium chloride solid and water. So we do the same calculation, delta S of reaction is equal to H2O plus standard state of magnesium chloride minus the standard state of HCl 2, 1, 2, standard state of magnesium hydroxide. Delta S of reaction is equal to 2 times 69.91 plus 1 times 89.6 minus 2 times 186.69 minus 63.24 delta S of reaction is equal to negative 207.2, and that is joules per Kelvin. So once again, we have a mole of gas going to no moles of gas, and since we have the loss of the gas state, entropy will decrease. So again, when you're looking at these questions, what you're making sure that you're taking into consideration, these are all standards, is just when it's a very obvious difference like 147 or 207, it should be easily figured out by looking at the equation that makes sense. So for example, in a situation where we have a gas on one side and no gas on the right side, then what we should expect is a loss of entropy, and hopefully those will frequently agree. With the first one, when it was so close with only 15, it's very difficult to predict. So those are basically how entropy calculations take place.